acid-basis titration curve. Titration is a method for determining the concentration of a solution using another solution which is known concentration called standard solution. Equivalence point and endpoint are the terms that use in the titration process. The point for equivalent point is at which the reaction is complete. The number of moles of base is stoichiometrically to the number of moles of acid that have reacted. It means all reactants are used up till no more acid or base left in the solution at the equivalence point. Endpoint is the point at which the indicator changes color. The titration is stopped at the endpoint. The endpoint should occur at the equivalence point. Therefore, selecting suitable indicator with an endpoint close to the equivalence point is essential to obtain the ideal result in titration. Acid-base indicators. Indicator is a weak organic acid that has different color than its conjugate base, commonly used to indicate the equivalence point of an acid-base titration by its color change. Acid-base indicators has its own pH range in which the color change occurs. It means when it's in acid, it has different color, and when the indicator is in base, it has different color. So these are some common acid-base indicator and the color in acid and base and the pH range. pH range is range over which the indicator changes from the acid color to the base color. The pH range at the equivalence point is determined from the steep vertical portion in the titration curve. For example, pH range for phenolphthalein is between 8.3 till 10. The pH range for methyl orange is between 3.1 till 4.4. And the pH range for methyl red is between 4.2 to 6.3. This pH range is at the equivalence point. Different types of titrations have different endpoint of pH range, and it also has different suitable indicators for different types of titration. For strong acid, strong base titration, the endpoint of pH range is between 3 till 11. So the suitable indicators can be any indicator except thymol blue. For weak acid, strong base titration, the endpoint of pH range is between 7 till 11. Suitable indicators are phenolphthalein or cresyl red. The strong acid, weak base titration, the endpoint of pH range is between 3 to 7. Suitable indicators are methyl orange, methyl red, bromophenol blue, or chlorophenol blue. There are three types of titration curves in common: strong acid, strong base, weak acid with strong base, strong acid with weak base. We have weak acid, weak base titration, but it's not normally done because the equivalence point cannot be accurately observed because both are partially dissociated, so it's not accurately observed. So these three are the common types of titration curve. This is the step on how to sketch a titration curve. First, calculate the initial pH of an analyte. Analyte means the solution in the conical flask. Next, determine the equivalence point by looking at the volume and its pH. After that, identify type of pH jump, the steep portion in the curve, and finally identify the final pH. This depends on the titrant concentration. The titrant is the solution in the burette. The titration of a strong acid with a strong base. For example, a titration between 25 ml of 0.1 HCl with 0.1 sodium hydroxide. First, we have to calculate the initial pH before we start adding any bases. It means we only have 25 ml of 0.1 molar HCl in the conical flask. So, we have to calculate the pH of this HCl in the conical flask. Since HCl is a strong acid, the concentration of H3O plus is also 0.1 molar. It means all HCl 100% dissociation to become H3O plus and Cl minus. So the pH is equal to negative log H3O plus concentration. Concentration of HCl is equal to the concentration of H3O plus because 100% dissociated. So negative log 0.1, the pH is equal to 1. So first, put the point at 0 volume of NaOH because before adding any base, so 0 volume of NaOH, and the pH is at 1. Next, pH after adding 5 ml of NaOH. So we have to calculate after we add 5 ml of NaOH, what happened in the conical flask. Sodium hydroxide is added to the solution in the conical flask. It neutralizes the H3O plus in the conical flask. So the HCl reacts with NaOH to produce salt and ACl and water. If you look at this equation, balance the equation, 1 mole of HCl reacts with 1 mole of NaOH to produce 1 mole of NaCl and 1 mole of water. So first we have to calculate the number of mole because we have added 5 ml of NaOH. The molarity of NaOH is also 0.1. So initial mole, 0.1 molar, mole per liter is molar. The molarity times the volume. Volume must be in liter because the molarity is mole per liter. So to calculate the initial mole, molarity times the volume. The initial mole of HCl is 0.0025. The initial mole for sodium hydroxide is the molarity times the volume of sodium hydroxide in the conical flask, which is 5 ml, so 0.005 liter. Then initial mole of sodium hydroxide in the conical flask is 0.0005 mole. So the change of mole is 0.0005 mole reacts with 0.005 mole. Not all 0.0025 mole reacts with 0.0005 mole. This is because only 1 mole can react, 1 mole of HCl can react with 1 mole of NaOH. Here in HCl, we only have 0.0025 mole. We don't have 0.0025 mole in NaOH. We only have 0.0005 mole, less number of mole than HCl. So only this amount of sodium hydroxide will be used to react with HCl. So if you have only 0.0005 mole NaOH, it will only react with the same number of mole of HCl. So the remaining mole, because we have the number of mole in excess initially for HCl, remaining mole in that conical flask after reacted with NaOH is 0.002 mole, and that is no NaOH left after reacted with HCl. So the total volume is equal to 30 ml, 25 from the HCl, 25 ml in the conical flask, and then 5 ml of NaOH added from the burette. So the total volume is 0.03 liter. The concentration is mole divided by volume. So the mole remaining, we need to calculate the concentration after we have reacted the HCl and NaOH. So that is no NaOH left, so we don't need to calculate the concentration of NaOH after the reaction happened. Zero concentration. We only have the concentration of HCl. We only have HCl remaining mole. So mole remaining HCl 0.002 mole divided by the total volume of solution. Total volume is 30 ml. In liter 0.03 liter. So this is the new molarity of HCl after reacted with NaOH. It's not 0.1 molar anymore because this molarity has been used to react with NaOH. So it must be less. The molarity of HCl after reacted with NaOH must be less than 0.1, which is 0.0667 molar. Now we can calculate the pH. pH equal negative log H3O plus. We know that all HCl completely dissociated in water to become H3O plus and Cl minus because HCl is a strong acid. So if the molarity of HCl is 0.0667, it is the same as the molarity of H3O plus because all of this will be converted to H3O plus. So the concentration of H3O plus 0.0667 molar. So pH equal negative log 0.0667. The pH is equal to 1.18. And you can put at the point of 5 ml NaOH, pH is 1.18. Next, pH after adding 10, 15 and 20 ml of sodium hydroxide. As more sodium hydroxide is added, it further neutralizes the H3O plus in the solution. The pH at each point is calculated in the same way as we did before, and you will get different pH value for different volume of NaOH added. So this is how you calculate as we did before for 5 ml. Take the total volume and calculate the new concentration, and for the new concentration substitute into the H3O plus concentration and you'll get different pHs, and then you can plot for 10, 15 and 20. And then you add more 25 ml NaOH at the equivalence point. After you add 25 ml of NaOH, this is where equivalent point, because we know 1 mole reacts with 1 mole. So if you add 25 ml of 0.1 molar with the same molarity NaOH 25 ml, it's at the equivalence point. The strong base has completely neutralized the strong acid. The solution contains salt and water. So now calculate the remaining number of mole. If you calculate the volume for HCl and the volume for NaOH, they're the same and they have the same molarity, and then the change number of mole, this all of HCl reacts with all NaOH, so no remaining HCl and NaOH. In that conical flask, we only have salt and water, no HCl, no NaOH. So solution contains only Na plus and Cl minus, only this salt. So we have to calculate this salt, whether it's acidic salt, basic salt or neutral salt, because we need to calculate the pH. And we look at the salt, the Na plus from the strong acid, from the strong base, and Cl minus from the strong acid. Both do not hydrolyze, so this is a neutral salt. So no production of OH minus and H3O plus at all from this salt. So when there's no production, so the H3O plus equal to the 1 times 10 to the power of negative 7. So the pH is 7, neutral. At 25 ml NaOH, 25 ml HCl, the pH is 7. So plot here, pH 7. Next, you add 30 ml NaOH, add more, 5 ml more. So because previously we have 25 ml, add 5 ml more to get 30 ml of NaOH. That's after equivalence point, because equivalence point is at 25 ml. After equivalence point, we calculate the number of mole of HCl and NaOH, the HCl you'll get 0.0025 and NaOH 0.0030. So only the amount of HCl we have only 0.0025 and we have excess number of mole of NaOH because 1 mole react with 1 mole. So 0.0025 react with 0.0025 NaOH only. So we have remaining of 0.0005 mole NaOH. So this remaining number of mole, calculate the concentration or the molarity. Number of mole divided by the volume. Volume is 30 ml NaOH plus 25 ml HCl in the conical flask. You get 0.055 liter and the concentration is 0.00909 molar. So this concentration, that's why we don't need to calculate the concentration because you have 0. And the concentration of sodium hydroxide is calculated. So now we need to find the pH. pH for NaOH, we cannot find the pH straight away. We need to find pOH. So for pOH, we need the concentration of OH minus. We have the concentration of NaOH. So with NaOH is a strong base. Strong base dissociate completely to become Na plus and OH minus. 1 mole. So the concentration of NaOH is equal to the concentration of OH minus. So you just substitute that into the pOH formula and then you get 2.04. We need the pH, so 14 minus 2.04, you'll get 11.96. That is the pH when you add 30 ml NaOH. And plot here, at 30 ml NaOH, the pH is 11.96. Next, we add more NaOH and calculate as the same like before, number of mole HCl and NaOH and get the remaining number of mole. Calculate the new concentration of NaOH and we have new concentration of OH minus. Put into the pOH formula and 14 minus pOH equal pH 12.36 and you plot at the 40 ml of NaOH you get 12.36 pH. As NaOH added beyond the equivalence point, it becomes the excess reagent. So the OH minus concentration remaining neutralization is calculated. It will keep increase. If you increase the concentration of OH minus, the pH will increase after the equivalence point.